As a small exercise to get practice with Qibo, we are going now to implement one very important state in quantum computing and quantum information, which is one of the Bell states. The Bell states are states which are important because they are in what we call the maximally entangled state. In this specific case, we are going to build something which is the superposition of 0, 0 and 1, 1, because we are going to consider two qubits and we want to entangle them. This is important for many physical applications. So now what we are going to do is to find the proper quantum circuit to implement this state. So if we go to the code now, in order to implement the Bell state, we need at first to initialize a quantum circuit C equal to circuit, in which the number of qubits is 2, because we want 2 qubits. Then we need the superposition. And for this, we just add an Hadamard gate to one of the qubits. So C.add gates.h, and the target qubit will be the 0, 1. Now that the qubit 0 is in the superposed state, we can use it as control qubit in a control gate. In particular, we are going to use a control NOT gate, and we can add it to the circuit. So C.add gates.C0. We are going to use the qubit 0 as control and the qubit 1 as target qubit. This will be the most important step because the control qubit is here in a superposed state. So half of the time it will act on the qubit 1, half of the time it will not. Then we can finally add the measurements gate to the circuit. So we say C.add gates.m, and again we say star range 2, because we have 2 qubits. Perfect. So now we can print the final state and we see if we get what we expect. So we can type print C.execute with a certain number of shots equal to 1000 again. And as you can see, the state is what we expected. Is a superposition between 0, 0 and 1, 1. This means that, and this is basically the power of the entanglement, we don't need actually to perform measurements on both of the qubits, because we just need to measure one of them and then we will automatically know the state of the other qubit. For example, if we get as measure on the qubit 0, 0, then we know that also the second qubit is in the state 0. Finally, we can collect the frequencies and visualize them using the same plotting function. So we say frec equal to C with n shots equal to 1000 dot frequencies with binary equal to true. And then we can just pass to the visualize states function the dictionary frec. As you can see from this plot, is what we expected. So the two bars are basically equal. Half of the time we get 0, 0, half of the time we get 1, 1. Finally, we want to propose you some exercises, very simple exercises. And so we ask you if you can find which is the quantum circuit required to reproduce the other 3 Bell states that are listed here in this red box. Once you find the quantum circuit, you can check if the final state is correct by executing the circuit and printing the final state. Or you can also call again the plotting function and see with your eyes if half of the time you get 1, 0 or 0, 1 and so on. So now we can go on and we can see another Qibo feature, which are the parametrized gates. The most commonly used parametrized gates are rotational gates, and maybe it's easier to visualize them on the block sphere here. Rotational gates typically can be seen like rotations around the axis of the block sphere. So you set a specific angle, theta, that will be our parameter, and then you can manipulate the quantum state by rotating it around the axis of the block sphere. What we can do now is to go to Qibo and to implement some more flexible circuit in which we add some rotational gates. And as we are going to see in a few, we can manipulate the circuit by modifying the angles, so the parameters of the circuit. So now we can go to Qibo. And we already have coded here an example of circuit containing some rotational gates. In particular, this is an interesting architecture in which we are going to repeat a specific structure of the circuit. We use these layers here, this number of layers, in order to repeat 2 times, in this case, the same structure. In particular, the structure is given by these 5 lines here, in which we just set 2 rotational gates applied to each qubit of the system. So we are looping over the qubits. Indeed, we are setting gates.ry and gates.rz, in which we set q equal to q, which is looping over the qubits. And then we should specify also the angle theta. In this case, we start by setting theta equal to 0. Then we add a control gate, a CNOT gate, the measurements gates, and finally we print the circuit. As you can see from this drawing here, we have this pattern ry, ry, rz, rz, and the CNOT gate, which is repeated twice. Then we have the measurements gates. So by default in Qibo, we start our simulation from the computational 0 state. So since in our circuit here we set just rotation with angles equal to 0, we expect that we are not modifying at all the initial state. So we can check it by executing the circuit, collecting the frequencies and printing them like we did before. So we can collect an outcome object equal to C, executed with a certain number of shots equal to 1000. And then from the outcome we can also collect the frequencies. Frec equal to outcome dot frequencies. And if we do like this, then we can print the final state, outcome, and also we can call this function visualize state on the frequencies. And what you can see from the state and from the plot is that we are not moving from the initial state, which is the 0 computational state, 0, 0. Then we can go on, and now we can, in order to be sure our angles are still 0, we can, for example, collect them. Initial angles equal to c dot get angles. This is an interesting feature you can use while you are playing with variational circuits, so circuits in which you have parameters inside, in order to get the current values of the parameters. And then we can also save the number of parameters, and this will be useful in some minus. And params equal to len of initial parameters, so initial angles. And then we can print the initial angles. So print initial angles, and as you can see, we only have zeros. That was expected because it was our starting point. So now what we can do is to exploit the NumPy package we imported at the beginning of the lecture in order to generate a new set of angles randomly that we are going then to inject into the circuit in order to manipulate the quantum state with this new random set of gates. So we can start by setting the NumPy random generator seed by typing np, that stands for NumPy, random.seed equal to 42. This is just a way to fix the randomicity of the problem in order to allow you to reproduce the exact result we are going to get. And then we can generate the new set of angles. Angles equal to np.random. At this time, we need to define which random number generator we want to use. And in particular, I would suggest you to use randn, which is a random number generator function from NumPy, which generates numbers accordingly to a Gaussian function with center equal to 0 and variance equal to 1. This is not very important, but it's just to give you the shape of the density function from which we are sampling the points. And we generate n-params numbers, because we want to have one random number for each angle of the circuit. And then we set these angles into the circuit, and we can do that by calling c.setParameters, and you just pass the parameters, so in this case angles. So now, in order to check if we properly injected the parameters inside the circuit, we can call again the c.getParameters function, and we can see that now we have these random numbers inserted into the circuit. So finally, what we can do is to execute the circuit again, collect the frequencies, and then visualize the state, and we expect to see something different from the zero state. So the circuit can be executed as usual. We collect an outcome object. We set the number of shots equal to 1000, and then we can collect the frequencies by typing frec equal to outcome dot frequencies, frequencies, open close. Perfect. Now we can print the final state, and we can call the visualize state function, providing it with the frequencies. As you can see, the final state, which is represented here explicitly, is a combination of all the 4 possible states you can get after executing a system of 2 qubits. And from the plot you see the same, but in which you see also the frequencies of the specific possible solutions. So the next feature, the final feature we are going to see, is the Hamiltonian implementation using Qibo, and we are going to combine what we already know by trying to computing expectation values of some Hamiltonians over the final state we get if we execute a circuit. As final exercise of today, we want to combine what we already know from Qibo, so circuits, gates, how to execute the circuits, and so on, with some new feature that are the Hamiltonians. In Qibo you can implement your own Hamiltonian, or you can inherit some pre-computed Hamiltonian from Qibo. And then what we are going to do now is to try to compute the expectation value of this Hamiltonian over the final state we get if we execute a quantum circuit. In particular, we are going to take into account one very remarkable Hamiltonian, that's the transfer field Ising model. And we can so now implement it and then use the final state of a quantum circuit to compute the expectation value. So let me go to the code. And what we can do now is from Hamiltonians implement some specific Hamiltonian. In particular, we can type H, that's our Hamiltonian, equal to Hamiltonians.tfim, which stands for transfer field Ising model, and we set the number of qubits equal to the same number of qubits we used in the parameterized circuit, which is 2. We set Hamiltonians.tFIM with 2 qubits. Now we have our Hamiltonian, H. We can also collect and print some more information about it. For example, we can easily print the matrix form of the Hamiltonian. Can, for example, say matrix equal to H dot matrix, and we can print it. Print matrix. As you can see, we have a matrix which is 4 times 4 as a dimension, which is expected because it's the dimension of the system. Because 2 qubits is 4 amplitudes. And then we can also collect and print some more properties of the Hamiltonian, like the eigenvalues. Print H dot eigenvalues. As you can see, it's 2, minus 2, minus 2, 2, 2. We can print the eigenvectors, so H dot eigenvectors. Let me make some space here to visualize it better. Again. And then we can, for example, print the ground state. So print H dot ground state, which is this one. Finally, we can put everything together and we can try to compute the expectation value of this observable, so this kind of Hamiltonian, over the final state we get if we execute a quantum circuit. In particular, we can use the quantum circuit composed of rotations we defined above. So we can just type H dot expectation, and this will return us the exact expectation value. So thanks to the exact simulation. And we just need to provide it with the state. So we should call C executed dot state, because we need to pass a Qibo state object. As you can see, we get the expectation value, which is 0.069 and so on. In this lecture, we had a look to some more practical example. We built the Bell state, and now you also have some exercise to do about it in order to build the other Bell state. We played with parameterized quantum gates by constructing what we can define a parameterized quantum circuit, and then we computed the expectation value of a target observable over the final state you get by executing a quantum circuit. In the next lecture, we are going to introduce an important application in quantum computing, which is the phase kickback. This will be useful then when we will build the most important quantum computing algorithms.